All right, hi class. I hope you're doing well. Welcome to another lecture for circuits. Today we're going to talk about power with phasors, so AC power, and a lot of just definitions. So these are some things that come up with power generation, power plants, any of those kind of AC power things. A lot of industrial installations where you pay a lot of money for power. People want to know about these things. All right, so the general setup here is that we have a load, a general load with an impedance. So we're talking about phasors again, and ZL, where L is for load, not inductor. And there's a voltage across the load, V, and a current through the load, I, that are phasors. So since they're phasors, they're cosines. We assume the phase on the voltage is 0, but it works fine if you don't. It just simplifies a couple of things. So V is Vm with a phase of 0, and I is going to be Im with a phase of negative theta. The reason we put a negative in the I definition, current definition, is so that the impedance has a phase of positive theta. So pay attention that if you're trying to figure out what theta is, if you know the current, theta is negative, whatever the phase of the current is. If you know the impedance of the total load, theta is the phase of the impedance. So if we're calculating the power, power is voltage times current. So if we just multiply the two terms here, Vm, Im, cosine omega t minus theta. We can't do phasor multiplication here because both of these, if we go through the math behind the phasors, we end up with two e to the j omega terms that we factor out when we do phasors. So when we're multiplying sources, the phasor math isn't the way we usually do it. You get this half angle formula we'll see later. So we're going to keep it in the time domain for now, and this is power. So here again is power, and we want to use some trig identities to simplify this into a more applicable form. Doesn't look simpler, but anyway. So cosine omega t times cosine omega t minus theta. You can get this out of some trig identities. So this has the cosine of theta and the cosine squared of omega t. This has the sine of theta, cosine omega t, sine omega t. So this first parts are constant, and these are functions of time, the cosine squared and the cosine times sine omega t. If we think about this, cosine squared is always positive, so this one, if you were to graph it, you would have an average that's not 0. Because these go positive and negative, this term averages out to 0 in the long term. And average power is an important thing for your fuel consumption of your generators and things like that. So applying I think they're the half angle formulas, more trig identities, we go from here to this bottom form, which is kind of the standard form. This is the instantaneous power with AC current on our load, Vm Im over 2 cosine theta times this term 1 plus cosine 2 omega t, Vm Im over 2 sine theta sine 2 omega t. So we get this one. Again, these are constants here. This is function of time, constants, function of time. So the average power, like I said, is pretty important. And here you can see that these cosine terms and sine terms have an average of 0. So doing the average, which is the integral over one period of the power as a function of time, all of the time functions with cosine and sine drop away, and we're just left with this initial term. So it simplifies a lot if we think about the average power. The last use of definitions here is if we use our root mean square, the RMSV and RMSI that we defined way back when we were still in class. Look at your notes. The definition is just the amplitude divided by the square root of 2. If we put that in, then the average power is VRMS IRMS cosine theta. So you'll find in a lot of power plants they have a gauge for VRMS, a gauge for IRMS, and a gauge for this cosine of theta, which we're going to call the power factor. These three terms determine your average power. Average power is what you pay for when you pay your PG&E bill. If you're running a generator, it's proportional to how much fuel you're burning, that kind of stuff. So it's an important one to keep track of. All right, so here's the average power again. Here's the setup. These are all from previous slides, but we've got just a load with an impedance. The phase of the impedance is theta. That goes right into this cosine of theta. IM and VM give us IRMS and VRMS. So the three terms from our average power calculation. Again, the power factor is cosine of theta. Theta is sometimes called the power angle, but you'll hear power factor a lot more often than power angle. All right, so this is some more definitions. We're just trying to get into the field here. So we're learning the lingo of power plants and power generators, and actually people that use a lot of power. So if you're running like a Tesla factory, building cars, your power plant, the power use is really important. Anyway, so power factor, it's the cosine of an angle, and because that goes between plus and minus 1, people talk about it as a percentage. So a power factor of 100% means your power angle is 0. Cosine of 0 is 1. Power factor 70%, 70.07% is cosine of 45 degrees. Now the trouble with this is that the cosine of 45 and the cosine of minus 45 is the same. So just the percentage doesn't tell you what the angle is. So rather than just telling you the sign of the angle, we talk about if the angle is less than 0, then the power factor is said to be leading, because the current, the phasor for the current, leads the phasor for the voltage. So less than 0, leading. Greater than 0 then is lagging, because the current phasor is lagging the voltage phasor. So if you remember lead and lag from the beginning of phasors, it's this definition again. So what you might hear, not necessarily an old timer, but someone in the power industry, if they say 70% leading, that's how you have to define that power angle. That means that cosine of the angle is 0.7, which could be plus or minus 45.6. And leading says that the theta is less than 0, so we're at negative 45.6. So you have to know the power factor and whether it's leading or lagging to get the sign. Although that's already complicated, there's one more way that people talk about it. So leading, which is theta less than 0, is also called capacitive, because capacitors have theta less than 0, negative 90. And lagging is also called inductive, because inductors have positive phase, or things with mostly inductance will have a positive phase angle. So you might hear 70% leading, you might hear 70% capacitive, or 70% lagging, or 70% inductive when you're talking with people that hang around power plants or deal with this kind of thing a lot. So keep track of all that, or write it down on your sheet of notes. It gets very confusing, and we're just talking about the sign of the phase angle. All right, so a few more definitions. We've got average power already. We've talked about this, VRMS, IRMS, cosine theta. This is a new definition, reactive power. If you look in our book, it goes through a lot more details. But it's usually called Q, where P for average, Q is reactive power. It's VRMS, IRMS times sine of theta. So if you look back at the instantaneous power, if you use an impedance that's just a capacitor or an inductor, and the book goes through this in detail, if Z is just a capacitor or an inductor, then the peak power going into the inductor or capacitor is this VRMS, IRMS sine of theta. The average power, if you're giving power to a capacitor or an inductor, is 0 because they store it and then they release it. So reactive power averages to 0, so you don't use it in terms of fuel burned. So it goes in and out of the system, the load, but the average is 0. So at your house, PG&E doesn't charge you for this because it's not something you're burning on average. But because power companies have to size the power lines and transformers and everything to handle this and the average power, if you're an industrial power consumer, your power meter may charge you for P, which is actually what's doing the work in your factory, and also for Q, because that's a hassle for PG&E to have to deal with it. So you want to minimize your reactive power, your Q, because they may be charging you for it, and it's not doing any work. It's just going in, and you're giving it back. So, so industrial consumers get charged for Q, and we want to minimize that for industrial plants, and that's the point of an example problem coming up here. All right, so you can see we have a cosine term and a sine term up here. They look like components of a vector or sides of a triangle, so that's what comes up next. This is the power triangle, and it's just a way to visualize the average power, the reactive power, and the power angle, which gives us the power factor. So the hypotenuse here is VRMS times IRMS. That's called apparent power. The bottom leg here, adjacent, I guess, is P. It's the average power, or just the power, VRMS, IRMS, cosine theta. And then the opposite side here is Q. That's the reactive power, VRMS, IRMS, sine theta. So this is called the power triangle, and it's a way to visualize this is the average that you're using. This is how much is being put into your load, and then the load gives it back because we're alternating positive and negative. So it gets charged and discharged. In order to keep track of these, because this is the power that you're getting work out of, this is power that you're having to transform, and this is the hypotenuse of the triangle. Generally, these have different units. So we'll see apparent power, the hypotenuse, has the units of volt amps, VA. Volts times amps is watts, but they call it VA to make it clear that it's not the average power. The power, or the average power, P, we use watts because that's the main one. And then reactive power that averages to 0, but we still have to transmit. The reactive power has units of VAR, VA reactive. So you'll see these gauges around, and this is the reactive power gauge, and this is the average power gauge. So the math here hasn't been very hard. It's been mostly a lot of definitions, a lot of things to keep straight. So take some notes, find the chapter in the book, and we'll do some examples coming up next.